to improve their quality of life and increase their opportunities. I found this to be a little bit reverse to what we usually do, which is to look at a problem that needs a solution and work out the solution. Here, Walter has found a source of material and has looked for an application for it in order to develop a sustainable source of revenue for underdeveloped countries. And I found this to be a very interesting approach to an engineering problem. So, please go ahead.
Thank you. It's a pleasure to be here. When I noted how bad the weather was this morning, I asked my good friend Kent Dahlberg, where are all the pretty trees in the sunshine that you promised if I would come? And he said, oh, this will be good. If the weather's really bad, you'll have a better turnout this afternoon. There won't be temptation for people to go sit out and enjoy the good weather and the beautiful trees. And the good weather hopefully comes tomorrow, so it'll work out just great. Now, I am pleased to be here and to be able to share with you some, I think, exciting things that we've been doing at Baylor, which I think have the potential of being replicated in many other areas, because there have to be many different problem opportunities such as the one that I'm sharing. What we're doing is just one example. As was said, I'm for 24 years while I was at Texas A&M, I worked almost exclusively on high-performance composite materials, mainly graphite epoxy, mainly for NASA and the Air Force, stuff that costs $25 a pound and can only be used in very special, very performance-driven applications. So it's what I call high-performance, low-volume, very high-tech stuff. Things that are used, for example, on the shuttle and things on the rocket launches and things on fighter jets, and more recently, to some degree, on commercial jets, where saving a pound for the life of the plane generates that much more cargo that you can carry for the life of the plane, and so a pound saved is actually worth a lot of money. When I went to Baylor, part of the reason that I went there was I wanted to try to do some different things, which I could have done at A&M, but I sort of thought would be a good fit at Baylor. I wanted in particular to try to say I've had all this experience doing polymers and polymeric composites. What could I use that for to help people in developing countries? And at the time I went, I really didn't have any idea, because I knew developing countries did not need graphite epoxy composites, right? This is not going to solve the problems of the underdeveloped countries. And so I was trying to think, what could we possibly do? Well, about the time I had first gone to Baylor, an old PhD student of mine from Papua New Guinea, a fellow named Dr. John Pumwa now, first guy from Papua New Guinea to ever get a PhD in engineering. He is the department head of the of the mechanical engineering department of the one engineering school in Papua New Guinea, Unitech. And it's just a great guy. And he emailed me to say, can I come and do a sabbatical with you? And I said, well, maybe, John. I'd have to get some money. And to get some money, I have to have some sort of an idea of what we would do, so I have something to sell, more than I have a friend who wants to come visit for a year. Could you give us money? I mean, you need a better story than that, right? So he sent me back saying, well, I'd like to do tribology and wear. Now, those of you who aren't familiar with this, that really is talking about lubrication and wear. And why did he pick that? Because that's what he did his dissertation on 6 years earlier. So I wrote back and said, John, is there a big problem with wear in Papua New Guinea that we can try to address? And he wrote back, you know that's not true. And so I sent him an email saying, why don't you find something that we could work on that, if we were successful, might make a big difference in the lives of poor people in Papua New Guinea. And if you can come up with a good idea of that sort, then I'll be happy to go and try to sell it. So he comes back with 4 different ideas, one of which was doing something with coconuts. Now, I had no idea what the situation was with coconuts. I haven't known very much about coconuts. In fact, at the time, I didn't even realize coconuts didn't look like what you buy at the store. That's the nut inside of a bigger husk. So I am a total ignoramus when it comes to coconuts. But he tells me the following story, which has been now verified. If you go, for example, and read the book Made to Stick, which is about advertising, and how it changes paradigms and how changing paradigms changes culture. The first story in this book, Made to Stick, talks about what happened with coconut oil. In 1992, the vegetable oil people decided they wanted to get the market that was held by the coconut oil. It was widely used in candies. It was the only oil used in popcorn. It had a very huge market, and it was really the primary source of income for many poor coconut farmers around the world. The vegetable oil people wanted that market, and so they ran a very effective smear campaign in which they basically said coconut oil is bad for you because it's all saturated fats. Now, on the face of it, that does sound true, doesn't it? Because I've always thought saturated fats are all created equal, and they're all created equally bad. They said, in fact, one bag of popcorn that you might get at the movie theater, popped with coconut oil, has as much saturated fat as 3 Big Macs. Now, that's a really bad indictment because everybody knows Big Macs are really bad for you, right? And if it's as much as 3 Big Macs, it's got to be horrible. And sure enough, the campaign was very effective, and within a year, coconut oil just about disappeared from the candy market. It disappeared from the popcorn market. The demand for coconut oil went down by about 75%, and 10 million coconut farmers around the world saw their income precipitously drop by about 75%. So they went from being very poor to being destitute, which is really pretty sad. Now, if what the advertising campaign had said was true, then fair enough. If it really is bad for you, then we're sorry, coconut farmers, we're not going to eat it just because you need to sell it. But it turns out it wasn't true at all. In fact, short-chain saturated fats, such as you have in coconut oil, behave very differently in the body than long-chain saturated fats, such as you get from animals. 22 carbon atoms versus 12. It metabolizes without any enzyme. They use it in Olympic athletes' pep drinks before and after their event. It burns without an enzyme. It's really, really a good fuel. It has antibacterial and antiviral characteristics. The main component in coconut oil is lauric acid. Lauric acid is a fatty acid of 12 carbons chains, 12 carbons in a chain. It's the very same element or compound in a mother's breast milk that helps young babies to avoid disease until their immune system becomes more tuned up and functional. But a mother's breast milk has 10% lauric acid. Coconut oil has 52%. You can put it on warts on your arm that are viral warts, and they will go away. If you have ear infections that don't seem to respond to anything, put a little coconut on that. It sounds like I'm selling snake oil, doesn't it? But trust me, it does all kinds of things. It's great for hair and skin care. It's got a lot of wonderful characteristics, but it was absolutely false that it was really bad for you. And sadly, that campaign was really, really effective, but it was predicated on misinformation. So what did we use instead of coconut oil? Hydrogenated vegetable oil. Now, what do you know about that if you pay any attention to health foods? Hydrogenated vegetable oil has trans fats, and trans fats are almost like poison in your system. Today, the maximum recommended allowable is 2 grams per day, which is essentially none. Okay? Some cities have even banned trans fats, and that's what we substituted for coconut oil. Does coconut oil increase your cholesterol? The answer is yes. It increases your HDL, your healthy cholesterol, not your LDL, which is your lousy cholesterol. That's the easy way to remember those. So, but I'm not here to talk about coconut oil today. I'm here to explain how I got into coconuts and coconut oil. I don't have $10 or $50 million to go solve this problem. So the question is, what could I do? Well, my friend John Pumois said, let's make coconut biodiesel. Everybody's getting into biodiesel today, and so I thought, well, that sounds like a sort of a good thing to do. We actually did that, but we didn't do it with the idea of selling it in the main city in Papua New Guinea. We did it with the idea of doing rural electrification. There are many places in rural Papua New Guinea where people have no electricity, and the cost of running electric wiring and grids to these remote areas is going to be prohibitive for almost the foreseeable future. These people also, by and large, are villagers who have no real currency, no money to buy stuff. So we thought if we could use coconut oil to make biodiesel, then we could provide generators. That's a one-time cost, and they could be self-sufficient in creating their own energy. And that would dramatically change the lives of poor villagers. The problem was that this project worked with methanol. We could make great biodiesel, but the cost was $11.70 a gallon, so that's not going to work in major cities. Would you pay $11.70 for biodiesel? I'm not that green. It does smell good, okay? It smells really nice, but who wants to pay that much extra so their diesel engine will put out smell that smells like coconut as opposed to diesel fuel? I don't think very many people are going to say, let's do the cost benefit. No, it's not, benefit's not big enough. But what we were trying to do was not to do that. We didn't really plan to try to sell it in big cities because we knew up front the value of coconut oil as a cooking oil in developing countries was still quite significant, $3 per liter. We thought if in rural villages they had their own coconuts, they could make their oil, and for them it's actually free, and they don't have a good market to sell it in a rural village. And if they could make ethanol, they could use the ethanol to make biodiesel. Now the problem is if it has moisture, it doesn't work, and we weren't sure how much moisture could be tolerated. So we started with 100% ethanol, and we made great biodiesel. We did 0.5% water, 99.5% ethanol. You have to use ethanol or methanol to make biodiesel. That worked. We got to 1% water in the ethanol. It did not work. The water poisoned the chemical reactions. And so what we concluded was there's no way in a rural village to make 99.9% pure ethanol. And so making biodiesel in rural villages to do rural electrification is simply not going to work. It's a good example of where you can actually burn pure coconut oil in diesel generator and it works fine, but you have the problem of starting and finishing. And so we made a generator where you could use the heat from the generator to heat the oil, but you needed diesel fuel to start and finish, and getting diesel fuel to rural villages to people who have no money to pay for anything wasn't a solution either. So along the way, we concluded what we were trying to do with biodiesel didn't work. It worked technically, but it did not work economically. But I learned a lot about coconuts. I learned about coconut farmers. I started taking a tablespoon of coconut oil every morning on my toast. My wife cooks all of our eggs and stuff in coconut oil. So that was a partial success for the program, but more personal than helping any poor coconut farmers, because I'm not a big enough consumer to change the market. But I also became acquainted with the plight of the coconut farmer and wanted to see what we could do to help. Now, the band that I've drawn here in this picture tells you where coconuts grow. It's plus or minus 20 degrees from the equator. In the figures here, the red represents where 75% of the people in the country make $2 a day or less. The gray represents where we don't have sufficient data, and the darker orange represents 15 to 35% live under $2 a day. Now, if you look at that map, almost everybody is either very poor or we don't have the data. So it's interesting, where there's lots of coconuts, there's also lots of poor people, and it turns out that many of the poor people happen to be coconut farmers. So our thought was, let's look at the whole coconut, not just the oil, and figure out what can we possibly do with the different constituent parts of the coconut that would provide additional economic opportunities for the coconut farmer. As we worked on this project, people often say, how did you ever think of coconut fibers for composites? And I like to say, I'm such a good material scientist, I thought about all 35 natural fibers and I explored all the different properties, and we concluded coconut fiber is different and better, and here's the reasons. Nope. That isn't the way we really did it. We started by looking for an abundant, renewable resource owned primarily by poor people in developing countries. And then said, what can we do to make that worth something? If it's abundant and underutilized, and it is, then this becomes for us our trash to cash program to help poor people in developing countries. And so in essence, that's what we've been trying to do. Now, I had a little bit of a fear at the start that maybe the reason nobody uses coconut fiber for anything is that it has no good properties. I mean, that is a possibility, isn't it? You can say, gosh, if it had really good properties, then why didn't somebody figure this out a long time ago and do something about it? And the answer is probably because the poor coconut farmers aren't the people who are able to do that themselves. They aren't the people who are able to afford to have it done. And in most of the countries where coconuts are readily available, the government itself is fairly poor. So in fact, as it turns out, this is one of those interesting rocks that nobody's turned over, partly because nobody has tried. We went to a conference last summer in Thailand, and we were the only people there from the United States. I've gone and given talks in the Philippines and Indonesia. When I went to the Philippines, to the main university there, they said, "What are you doing working on coconuts in the United States? They don't grow any there." Now, that's a fairly good question, isn't it? It's not easy to get funding for this project, because that's what USDA says, too. You want us to help pay for you to do coconut work? Well, shucks, we can't do that. It's not grown in the United States. Okay, well, we'll come back later and say, where did we finally get some funding? Because we did get some funding. You can't go too far down the road without funding. There are basically 50 billion coconuts per year. That's an abundant renewable resource. The coconut husk is that part that surrounds the nut, and it is probably about a third of the biomass. About 1 1/3 pounds per coconut. So that's a lot of biomass. And probably 85% of the husk are not used at all, and in worst case are burned, which adds more pollution to the environment. So it's bad in the sense that it's not used, and it's worse in the sense that if it's burned, it's actually negative. The average coconut farmer's annual income is $500 per year. They typically have 5 or 6 children. Can you imagine living with a family of 7 or 8 on $500 a year? It's not very pretty. Here's a picture that I took when I was in Indonesia as we visited with coconut farmers and sat on the porch and talked to them and asked them about their lives and what they got for their coconut meat. They open the husk, then they open the shell. When you go to the store, you just buy the nut, you don't buy the husk. And they open that up, they dry out the white meat, they sell the white meat to somebody who then presses it and makes oil, and they get 5 to 10 cents a coconut. So they don't do very well. This is his family, and you can see they don't look like they're overfed. You can see in the background all the coconuts that they're getting ready to work on. Most coconut farmers have 2 to 4 acres, and every time they have a family with 2 or 3 sons, the acreage gets smaller and smaller and smaller because none of the children go to school. On $500 a year, they can't afford to pay for books and uniforms, even if the education itself is free. Just the auxiliary costs make it out of reach. So what's the son of a poor coconut farmer going to do? He wants to be a coconut farmer like his dad, but that means the land keeps getting divided, so these people get poorer and poorer. Here's a picture I took in the same area of just a bunch of kids that are so cute and friendly, and I saw them playing with sticks and rocks and stuff, and I thought, wow, they are having as much fun as my grandchildren with all their very expensive, video games and stuff. It's amazing how they seem to be happy, even though their lives are in many ways very challenging. And you can see one of the little girls didn't want her picture taken. So the rest of them seemed quite happy when I said, "Can I take your picture?" And all of them grouped up and smiled and looked real excited to have their picture taken, because they probably don't have gringos from overseas come and take their picture very often, or maybe anybody for that matter. Okay, when you travel in developing parts of the world, this is what you'll find everywhere, that there's coconuts. And the question is, why are all the coconuts piled up like that? And the answer is because there's somebody who is basically making coconut oil, and the process is to take the husk, which is about this big, and break it open, and inside of that is a nut, which is about this big. This is what you would see at the store. They just don't ship the husk. It's not edible, it's not burnable, it's not very good for much of anything. So they just take the husk off. They may sell the nut, or they may open it up and produce coconut oil from it. When they do that, what do they do with the husk? They just pitch them and make great big piles. And this is not, I didn't look for the biggest picture I've ever found. I've got 50 pictures like this, 50 different pictures. Every place I go, it's just a huge waste disposal problem. In Vietnam, a lot of the people there are throwing them in the rivers, and now they are clogging up the rivers and creating problems there because they didn't know what else to do with them, and they don't burn very well. If you looked at the inside of a coconut, if I just did a cross-section, it would look something like this if I took a nice big bandsaw and cut through. you can see how big the husk is. The part that you're accustomed to seeing is the shell, the dense hard part that goes around the outside. I often have wondered why they didn't use coconuts for cannonballs in the old days, because this stuff is really, really hard. If you take a coconut and just thump on it, you can think, man, if you hit somebody with that, that would really knock them out really good. We actually measured the hardness. It is 5 times harder than maple, 10 times harder than pine. It has a density of 1.2. When you put it in water, it sinks. Interesting wood that sinks. That's why it's so hard. It's so dense. We'll come back later and maybe mention a little bit. There are some great things we can do with that we're working on. Okay, then you look at the husk, and out of the husk, when you process this, you will get 2 different constituents. One of these is a rather dusty, it almost feels like fine grains of dirt material that comes out of the husk, and then the fiber. And we get about half and half. It turns out the pith will absorb 10 times its weight in water. And when I first heard that, I did not believe it. I thought just people trying to sell coconut pith. But it's easy to check, isn't it? So we got some pith, we went and put it in water, and sure enough, it absorbed 10 times its weight in water. And now I'm thinking, how can it do that? There's not that much surface area. How could you get it to stick, so to speak? And then we put it in the scanning electron microscope, and what we found was it's actually like hollow beads. It's not like solid particles. If it were solid particles, it would not absorb that much water because it would simply be able to, with adhesion, hold it to the surface. But you can't get that much water on the surface unless it's nano-sized particles, maybe. So the fact that it acts like little hollow beads means it, by capillary action, absorbs water into the beads and stores it. Now, what are some good applications for this? If you were thinking of what would be useful for something that absorbs 10 times its weight in water, that would be a good application. The first thing we thought of was diaper fill. Okay? When you talk about what are the most awful things that fill up the landfills, one of the most egregious things is what? Diapers. And if you have a baby, you may be putting 10 of those big things or so per day into the landfill. And it's all done with synthetic stuff. So we got some diapers, and we opened them up, and we took the stuff out, and we put water in it, and gosh, it absorbed 50 times its weight in water. And I thought, that's really amazing. It just looks like a expandable foam almost, and it absorbs a huge amount of water. So we thought, okay, plan B is let's do gardening applications where you want to have potting soil. And so, in fact, we have already found that this is already being done to some degree, so we don't have to invent this. I talked to one major chain of gardening stores that sell potting soil, and they told me if we could provide it, they would be happy to buy 800 shipping containers per year worth about $10 million. So I thought, that's good. I want to sell everything in the coconut, right? Isn't that the way to do the biggest, do this job right? Everything has to be useful for something. And so coconut pith is a great application for potting soil, which always will have some peat for nutrition. It will have some water retention substance, and then it'll typically have ground up cheap bark or something just to keep the price down. And so this is a really excellent application. We don't need to do anything on this. We're still thinking about the diapers, though. We're going to figure out how to make that work. But the potting soil works right now. Now, what about the coconut fiber? We've talked about the shell. Let me just mention, because I'm not going to come back to this, what can you do with the shell besides use it for cannonballs? Okay? It's got a hardness that's really, really high. It's also pretty brittle. So if you hit it with a hammer, it cracks open. So if you were to grind it up, you might be able to find some good applications using it as a reinforcement in engineering plastics, for example. If you want a more green engineering composite, then that would be one possible way that you might do that. Now, let's talk about the fiber, because that's where we've really put in most of our time and effort and where we've gotten some really, really exciting results. First of all, what is it about core fiber, which is what a coconut fiber is called? I'm going to call it core fiber from here on out. Core fiber is one of 35 natural fibers, and if you say, well, we're going to try to do something that utilizes natural fibers, the question is, so everybody's trying to do something using natural fibers, and there's lots of other natural fibers out there. Kniff, flax, bamboo, there's a lot of different natural fibers. What is it about coconut fiber that might make it distinctive and give it a competitive advantage? So we began to explore that. That's now where I get to use my material science, okay? So we go and we look at the coconut fiber and we find out, first of all, it's the only natural fiber from a fruit. The only natural fiber from a fruit. So that means it ought to be different in some ways, and sure enough it is. One of the distinctives is that it is very high in lignin content. It has about 35% lignin content, which is the highest of any natural fiber by a lot. Most natural fibers are basically rich in cellulose. It has a large diameter, about 160 microns, which gives it a high flexural stiffness, and it has a high elongation to help the husk protect the coconut on impact. Now, if you look at each of these, let me share with you why coconut fiber has a different combination of properties. I'm not saying it's better than all fibers for all applications. It is not. Material science is always a game of trade-offs. You get more of this, you get less of that. The question is, what are the family of properties here, and why might they be actually better for applications that I'm looking at, or what applications would that be better for? What is the function of the coconut husk in nature? Coconuts are typically at 60 to 80 feet up on the coconut tree. One of the leading accidental causes of death in developing countries is the coconut falls and hits somebody on the head. So if you're in developing countries where there are coconuts on the trees, don't walk under the trees or look up often, okay? They can fall on your head, and they're about 4 pounds. 4 pounds at 60 feet represents a lot of kinetic energy. I don't know what the impact resistance of your skull is, but it may not be more than 240 foot-pounds, right? That's a fair amount of energy. And we usually don't wear helmets. Okay, so the first function is when that husk with the nut inside hits the ground, the nut is not supposed to break open. So it ought to have very good impact properties. Now, to have good impact properties, it has to have good ductility. And good ductility is, in fact, what it has. It should also have a good flexural stiffness. And it provides that flexural stiffness by having a large fiber diameter. The properties of the coconut are not accidental. They're what they need to be to provide these functions in nature. If you look at most other natural fibers, like kniff, for example, the elongation is 1 to 2% versus 25%, which is a huge difference. So that's a big advantage. Why does it have the high lignin content? If you know anything about lignin, it's one of these things that nobody wants, typically. When they make newspaper and they use cellulosic materials, lignin is part of what they're trying to get out of there. It has the chemistry of a phenolic resin, and it is considered a nuisance. I've heard people say that they've made everything out of lignin but money, okay? And hasn't seemed to find a home for anything. But in our application, it's actually quite desirable because phenolic resins are probably one of the very best synthetic polymers for burn resistance. Phenolics don't burn very well. Cellulose burns extremely well. Cotton burns extremely well because it's high in cellulose. In fact, if you know anything about cotton clothing for children's pajamas, it has to be treated because it burns so well that a child's pajamas can just go inflamed so quickly that you couldn't get it off in time to keep the child from being significantly burned. Now, why would it be like that? Because it's protecting the coconut seed, the nut, and where you have fires and other things, the coconut husk will provide some protection so that all the seeds don't get destroyed. It also is indigestible for microorganisms, by and large. No self-respecting microorganism can make a good dinner out of lignin And the lignin tends to be pretty continuous in the coconut fiber, and so it means we don't have problems with microorganisms creating smell problems in coconut fiber. Now, in a natural environment, this is to prevent what? All kinds of pests and things from wanting to get into that coconut husk because it would like to get the coconut meat, which is very nutritious and would be very attractive. So it's providing protection in nature, but it also helps us. An interesting example of what can happen, Mercedes-Benz, who always wants to be first in everything, and sometimes it's dangerous to be first. Okay? If you're out front, sometimes that's the guy that gets shot when you're out exploring. Coconut fiber was first used, not coconut fiber, flax fiber was first used as a natural fiber by Mercedes-Benz in the door panels of Mercedes-Benz cars. The flax is 95% cellulose. Cellulose is a very attractive meal for microorganisms. If you have any humidity, you can have enough humidity and enough nutrition to grow little colonies, and pretty soon those early Mercedes-Benz that they used this in began to smell like restrooms. Now, if you pay $50,000 for a car, you do not want it to smell like a restroom, right? You don't want stinky odor from microorganisms that are expelling that. So the picture I showed you a minute ago of the coconut piles, I knew that this was going to do well. Oops. Because when I go to places like this pile may have been sitting there for 6 months, half of the husk are up, water's coming into the husk, lots of sunshine. This is tropical areas. If you're going to grow anything, you would grow it here. You would think standing by this, it would smell like, think what a pile of garbage would smell like. If you put a pile of garbage out here and left it for 3 days, what would it smell like? It would be unbearable. It would be absolutely obnoxious. There is no smell beside this kind of a setup. I put 100 pounds worth out on the back part of my backyard, so it gets sun and rain, and it gets sprinkled by my sprinkler system twice a week. And if it's going to grow anything, it would grow it. It's been there 18 months. I cannot smell anything when I'm standing next to it. And if I get my nose up close, I can smell only, it smells like a coconut fiber. It has a very slight fiber smell, but not an odor. Yeah. Well, unless you forget to turn it? Yeah. This hasn't been turned, though. That's what I'm saying. Nobody's turned this, and nobody's turned my coconut. My coconut fiber's been sitting there in a big pile, okay, from beginning to end. And if it's in your door, where microorganisms can access it, nobody's going to be turning it either. So I think the point is that anything that will grow microorganisms is going to potentially produce odors, and odors are one of the big liabilities that you have to persuade automotive companies or other applications that's not going to be a problem. Okay, so here's what we have. It's very stiff in bending because it has a large fiber diameter. Most fibers are about 50 microns or less, and this bending stiffness depends on the diameter raised to the 4th power. So if my diameter is 3 times as big, it means my stiffness is 27 times as big for that part of it. It has 25% ductility. It's very burn resistant. It's microbial resistant. It's moisture resistant. It's odor free. It's hypoallergenic. Okay? Sounds really good. Now people often ask, how would this be for making fabrics for clothing? And the answer is, first of all, it's a stiff fiber, which probably isn't very comfortable for clothing. But the worst part of it is, if you look at the fiber in the electron microscope, it has a very rough surface texture, okay, which makes it scratchy. So the only application I thought of for clothing would be underwear for terrorists. And if you want to get terrorists to confess, make them wear coconut fiber underwear, and within a week they will confess almost anything. Okay? Now maybe people would consider that inhuman or inhumane or whatever, but it isn't going to be good for that application in general. Now, here's what we have. We start with the coconut husk. Okay, let's see. Okay, so that's just a piece of the coconut husk. And when I process that, which we want to do in country, then I will end up with pith, that's the stuff that absorbs 10 times its weight in water, little particles. If you held it in your hand, it would feel like very finely grated dirt. And here's some coconut fiber. I'm going to then take the coconut fiber and I'm going to combine it with a recycled polypropylene. Now I say recycled because I've got to have something in there that is a binder fiber, and natural fibers will not serve that purpose of binding things together. So I'm not using something that's 100% green, but by using something that's recycled with something that's natural, it's a very environmentally friendly product compared to what's currently used. What's currently used is polypropylene with polyester. Okay, so when I combine these two, and this is going to be done in some rather large equipment that's done at Hobbs Bonded Fiber, who we partner with on this, and it'll take fibers that they need to be clean 2 to 3 inches in length. They will be sprinkled onto a conveyor belt until they reach a certain thickness, and then they go through a roller to compact them, but now they're all still in plane, and the felted material is not very cohesive. Then you can do needle punching with thousands of needles, literally 16,000 needles punching over and over and over again. So a lot of the fibers get like that. And what that does is it simply makes the felted material much more cohesive. Incidentally, the stiffness of the fiber is already being utilized in something you may own. If you buy some nice doormats made out of natural material, the natural fiber used for doormats is always coconut fiber. And the thing I like about it is you can clean your shoes on it because it's very stiff, but it can sit out on your front porch in the rain and sun and all. We have one that's 5 years old. It still looks really, really good. But we're not making door things because people are already making door things. That's another application, but there's not enough door mats to use up all the stuff. Okay, so at Hobbs, they can actually make rolls that are 60 inches wide and 150 feet long. They already supply the automotive industry. They're just supplying it more typically with polyester and polypropylene made into a non-woven fabric composite that looks like this. This part is then compression molded into making a trunk liner, and that's a trunk liner off of a 2009 Chevrolet Malibu, exactly the car that I own. So there are a number of places where you can use these in automobiles. The trunk lid liner, all of the interior parts of your trunk, door panels, headliners, dashboards, mud flaps. Under the hood applications, there are probably 100 pounds worth of non-woven fabric composites in those cars. So that's a lot of stuff. It's a great big market. We don't want all of it, just 20%. Okay? Now, at a higher magnification, this is what our non-woven fabric composite looks like, and I think you can see there it is not woven, right? Now, it looks like on the first glance that there is a lot more polypropylene than coconut fiber. The coconut fiber is the more light brown. The polypropylene is the clear. The reason it looks like that is that the polypropylene is about 1/3 the diameter, and so it takes 9 fibers of polypropylene to equal the same mass as 1 fiber of coconut. So it gives you the illusion. This is actually 50-50 by mass, and we simply weigh it, put it in the hopper, it gets completely blended, and then it gets deposited. Now, after we have the felted material, which is nice and flexible, like a fabric would be, you can put it in a compression mold that has a certain shape. If you preheat it, put it in the mold, and squeeze it, the polypropylene will actually flow, and as it flows, it will essentially stick everything together, and this is what it looks like if I do that at a lower temperature. And now it becomes rigid, and it will have the shape, for example, of my trunk liner, or it might have the shape of a door panel, or it could have the shape of a dashboard. So I'm starting with a felted material, heating it up to a temperature where the polypropylene will flow, then pressing it into a mold, or putting it in a mold and pressing it into the shape I want. When you cool it down, it's now rigid. So this is the way everything gets made in the auto industry. If you look at parts like this, they basically take pieces like this, they heat them, put them in a mold that has this shape, and they press it, and out comes the part. Now, if I go to higher temperatures, this is what happens. The previous one was 170C. This is about 190C, and at 190C, what's different? The polypropylene is significantly more melted. The whole thing has achieved a higher density. I'll show you in a few minutes how that affects properties. This one is going to have a higher strength. Why? Because things are really glued together much better than they were in the preceding one. Now, if we look at how the strength varies with density, this is all coconut fiber results down here. And as you would expect, as the density goes up, the strength goes up. Now, what do I mean by strength? Ultimate tensile strength, I take a sample with the bigger ends, dumbbell shape. I pull on it. I measure the load at which it breaks, divide it by the cross-sectional area, and I get the load in, say, newtons per square meter or pounds per square inch. As I go up in density, I've got more and more of that coconut fiber that's being, in a sense, webbed together with the polypropylene. And the more of those fibers I have per unit area, the more load it'll take. So as density goes up, so does strength. Up here is what they're currently using. And it is stronger, but it also is stronger at a much higher density. And you would expect it to be stronger if it's at a higher density. Now, I'm not so much interested in strength as I'm interested in flexural modulus, because all the applications I'm looking at are ones like this. If I were to put two supports here, put a load here, I'm interested in how much it deflects. When you put your arm on the armrest on your door, you're not going to break it off, hopefully, okay? Not unless you push on it really hard. But you will feel it. If it deflects very much, you would feel like, well, this is kind of cheesy. You know, I should have gotten a different or more expensive car. I mean, all the parts are just way, way too flexible. So it's flexural modulus they were looking for. Now, the flexural modulus of the material measures the stiffness of the material independent of geometry, okay? And again, as you would expect, the flexural modulus increases with density, but it's lower than what we get for the current material, which is PET. So you say, well, shucks, I guess we're out of business. This isn't going to work. But not so fast. The flexural rigidity is what I'm interested in. Flexural rigidity depends on not just the properties of the material, but it depends on the geometry. If I have a block like this, or a 2x4, if I put it in this orientation and bend it, it will be much stiffer than if I put it in this orientation, right? You put a 2x4 in the 4-inch width, it's much stiffer than if I do it in the 2-inch if I roll it over. It turns out that the I term that goes into the flexural modulus times the geometric component of flexural rigidity. The I is a function of the width, that would be this, times the thickness cubed. Now, if I use polyester and polypropylene, it's going to be twice as dense, which means it's going to be half as thick, right? If I'm using the same 1,000 grams per square meter, if it's twice as dense, it means it's going to be half as thick. If it's half as thick, according to this, and the I part is a function of thickness cubed, then it means that the I part is going to be lower by a factor of 8. So when I combine those two, here's what I get. If I look at flexural modulus by itself, okay, versus density for polypropylene versus coconut fiber, it looks like polypropylene is better. Polyester is better. Polyester. If I look at the EI term, which is what I'm really interested in, for a given 1,000 grams per square meter, this is all the results for coconut with differing percentages of coconut fiber, and this is what we get for PET polypropylene. Now, what does that mean? That means we win, right? Because I'm only interested in how flexible is the part, not the pure properties of the material. Once you take 1,000 grams per square meter and compression mold it into something, what's it going to look like? Okay, how stiff is it going to be? And the answer is, depending on how much coconut fiber, we can be from twice as good to maybe 3 times as good. So now we can say we can be cheaper, we can be greener, and we can have better performance. If you can't sell that, you're a really bad salesperson, okay? And I'm a really bad salesperson, and we are getting very close to getting some major deals with major automotive companies and their parts makers. Okay, this simply gives the flexural modulus as a function of density. One of the things we learned recently, there's a machine direction as the conveyor belt goes by, so the fibers are not completely random. So the properties in the machine direction are a bit different than transverse to that, but this is fairly typical of what you would also get with polypropylene polyester. This is results that we had 6 months ago, and this is results that we have today. It shows that if we work hard on getting the processing better, we can make the properties a lot better. And people were quite interested when we were down here. That was the last graph I showed you, but we're getting better and better and better at figuring out how to do this in a way that gives really excellent performance. One of the interesting things that comes out in this is, what's the optimal thickness, or let's do it a different way, what's the optimal density to use? If I use too low a density, my flexural modulus is too low. If I use too high density, my thickness is too small. It turns out there's a place in between where I get the best combination of good flexural modulus and good geometric stiffness. And so that turns out to be at about 0.4. Okay, there's lots of different car parts that you can make. We're working with one company who's already making door panels. I can't show you pictures. I can't tell you who. Why? Because I'm under an NDA and I don't want to be sued. Furthermore, these are my friends who I hope will become my customers, right? And so I can't show you, but it's really, really cool to see some of this stuff already being made into car parts. So here's some of our applications, door panels. Now, you would say, well, if you did your coconut fiber, it's not going to look like that, but that just has finishing cloth on it. So our door panel looks exactly like this for a very, very fancy, pretty high production sports car, because all of these are going to have a 1,000 gram per square meter or maybe 1,500 gram per square meter piece that is structural enough, and then maybe 200 grams per square meter of finishing cloth, which could be a vinyl that looks like leather. If it's a really expensive car, maybe it is really leather. Or a pure polyester finishing cloth that just makes it look sort of fluffy. So depending on how they finish it off. But our part looks exactly like this, except if you turned it over, if you pull that off the door and looked at what's behind it, it would be our coconut fiber composite. So very exciting. Okay, so what have we already done so far? Well, this is probably details that aren't so interesting to you because you don't know what the fog and smell test is and all these other things. But the point is we have passed all of the different certification tests. Now, the automotive companies, once they're satisfied that price-wise, formability-wise, performance-wise it does well, then they will run their own set of tests to validate this, although some of these have actually been done by automotive companies for us. Pass the fog and smell test. You may wonder, what is the fog test? It turns out that polymers sometimes have low molecular weight volatiles, and on a hot day, those can be emitted and leave a film, an oily film, on your windshield. I worked one summer at Lawrence Livermore Labs in California, and it got to 115 degrees outside and probably hotter than that in my car. And I had lots of problems with little oily residue where my dashboard was actually emitting low molecular weight organics. And so you have to pass the fog test. You can't leave residue. You have to pass the smell test. It can't smell bad. And they run it through a bunch of cycles to give it every chance to smell bad. And then it has to pass. It has to pass the burn test. We do really good on the burn test. When we do our stuff, the only thing that burns is the polypropylene. The coconut fiber doesn't burn at all. If we use 80% coconut fiber, it will self-extinguish, which is really, really good. Okay, so we're looking at having production partners who we will be buying from. We're going to help provide them with what are our specifications and how to produce it to get it exactly the way we need it. We want to do this in a way that we will meet all international fair trade requirements and hopefully exceed those to be sure that the communities that we're working with are going to be very, very significantly benefited by what it is that we're doing. Okay, how do we keep other people from coming and stealing this and selling it at a cheaper price where they don't give the coconut farmer anything? And the answer is intellectual property. We have a patent that we've applied for that would allow us to have exclusive use of coconut fiber composites, and that will allow us then to say nobody can use this technology without licensing it from us, and we will only, as a part of our licensing agreement, they will have to let us be the supplier of the fiber, as well as pay some royalties, okay, which Baylor gets, and which Wholetree, the company that has been started, will get as well. Okay, here's our small strategic partner. This is Hobbs Bonded Fiber. I didn't know these people existed because they aren't on a regular street because they don't sell to the public. They sell to General Motors and Ford and Hyundai and Honda and other companies. But they are a huge company that makes 15 million pounds of stuff per year already. And fortunate for us, because we have a little lab, we can't make anything. We can make experiments. And we can come up with good ideas, but you need a production partner. And they're it. And they're in Waco. Surprisingly enough, there are 8 companies like this in the whole United States. And who would imagine one of them would be in Waco? Not very likely, right? We're not very strategically located compared to Detroit. Although if some things get made in Mexico, then we're more strategically located. Okay, so let me simply close and open it up for questions. I know we're just about out of time, but maybe some of this has stimulated some questions about overall what it is that we're trying to do. Thank you for your time and for your attention. Yes. Let's suppose the target for a given automobile right now for trunk liners is 1,000 grams per square meter. Okay, on a trunk liner part, the thickness can probably be whatever. So they wouldn't necessarily specify that, but we would say, let's press it to give us a density of 0.4 grams per cubic centimeter. This is mass density, not areal density. Okay. If we made it thinner than that, which we can do, we can press it more, but it won't be as stiff. So the point. Correct. Now, sometimes they may have a specific dimension that they want. And for example, on the door panels that we're working with, they really wanted it to be a certain thickness. So what we ended up doing then was we ended up simply pressing it to a higher density. So we were way, way out here. Wait, let's see. That's areal density, pardon me. Okay, this is mass density. Yeah, we were actually out in this range just because they wanted a certain grams per square meter and they wanted a certain thickness. Was this quite as stiff as it might have been? The answer is actually not. It would have been more stiff at 0.4, but they actually said it has to be no bigger than this thickness. So sometimes for their own reasons that they're going to do a straight part substitution, and in a door panel the dimensions are more critical than they are in a trunk trim, for example. Yep, good question, yes.
Have you considered applications in fireproofing, insulation, materials, or
We are looking at a whole host of building material applications. I didn't talk about that today just for sake of time, but because of the unique combination of properties, there are a lot of interesting and pretty exciting possibilities.
are there already other green applications of materials for fireproofing, or is this?
I think most of the other applications, if they were using natural fibers, would have to be using them with some kind of a coating to give them better fire resistance. Okay, I've seen Kneff, for example, that has been coated or treated to provide that. Sometimes you can do it by putting flame retardants in the polypropylene sufficiently strong that it will simply inhibit the burning in general. But coconut fiber, in a sense, comes with its own flame retardant. So that's nice. It's just one less cost. It makes it more completely more natural. Yes?
So you mentioned at the beginning that product really focused on this was that you grew oyster sauce. I'm not really familiar with that. So I'm curious, when you look at a sauce you want, for example, do you focus on how much impact you have on like calories and oil? Is that something you're looking at going forward?
Well, we have already identified in all the places I showed you strategic partners who are absolutely committed to our triple bottom line business model, okay? And are as keen as we are to do this, not just to make it be a for-profit business, which it needs to be sustainable, but to make it be one in which all the different stakeholders are going to be benefited in an equitable way, okay? So how that gets done in different communities will probably depend a little bit on the local situation. As an interesting example, when I was in Indonesia, I was thinking we could just pay the coconut farmers for their husk because we will be selling at a price that would allow enough margin to say, okay, we can give them something for that. And the people that we were working with said, well, you may want to think more about that. Now, I'm just musing it. I want them to make the final decision because I'm not trying to tell them what to do. But they said, in the area that we were in, they said, if you were to give a windfall income to the farmer, instead of sending his kids to school, he might just get a second wife. And they explained, it's not that he doesn't like his first wife, it's a status symbol. To be able to say, I'm well enough off to be able to have two wives. But in fact, that would be really sad because I'd much rather him say, with that money, I can now send my kids to school. So one option in that area that we were looking at would be to say, if we can, they throw away 5 million coconuts per day, husk, 5 million. If we were able to generate big enough markets and make, that could be a big source of resources for the community. But we might, for example, have a school there, which there is not one now, and have vouchers so that the children of all the coconut farmers from whom we get husk get vouchers to go to school for free. We could provide fertilizer that would help them to double their yields. There are a bunch of different ways we can help them, only one of which is just give them cash. And again, in a way, I'm going to depend on the local people who are already there and understand the culture a lot better than I do to say, what's the best way to do this? We want to benefit and be a blessing to the community, but the question is, what's the best way to do that? And that may be different from country to country. Good question. Yeah, let's see if anybody else who hasn't asked one yet. Yes.
Obviously, one of your selling points here is that this is a greener product than other plastics that these car industries would use. So I had a couple of questions about the manufacturing itself. These recyclables, polypropylene that you use, could they theoretically also be recycled in a conventional polypropylene cycle? I mean, could they just stay in that industry and be recycled?
I think it's just recycled carpeting and other such things. Yeah.
And then,
Yeah.
does the energy required to recycle it, because you are, mining for natural fiber, is that a lot higher than what you might see in the conventional plastic industry? If so, what energy are you using?
The energy it takes to make polypropylene would be quite high compared to the energy it takes to recycle it, okay? And the energy it takes to do what we're doing with the compression molding is the same independent of what materials I'm using. So if you did a complete sort of a carbon footprint type analysis, then you would find that it's extremely attractive, okay? We're not using any oil, okay? And the energy to recycle is a lot less than the energy to convert oil into virgin polypropylene.
And then can your product be used for other life cycles, or is it kind of like a use once?
We can probably regrind them and do other things with them. We haven't completely sorted that out yet. We hope to have that problem soon, okay, as we start using them. But if you put it in a car and it's there for, let's say, 10 or 15 years, it depends a little bit on how willing the salvage people are to separate out some of that stuff and what is the economic value of it recycled. But in principle, it can be ground and reused, maybe in injection molding or in some other ways. Probably can't be used to remake another part of this type because it's already a certain shape and it already has cutouts and so forth. To make a new part of any kind, you'd need a sort of a continuous fabric, not one that's already been utilized. So it can't be reused to make another door panel, let's say, but it could easily be ground up and reused in injection molding or doing some other kind of manufacturing.
And my last question is just what really needs at your
What?
production plant and what really needs what energy source?
I actually don't know the answer to that question. We have pretty, well, it should be oil, but actually it's more likely natural gas, but I think better than 10% of all of the energy in Texas is being generated by wind farms right now, because we have a real surplus of wind in West Texas, okay? And we're trying to capitalize on it. We've got some barren areas where there's nothing to block the wind, unlike New Hampshire where you may get wind, but you got lots of trees, right? And in parts of Texas, we have lots of trees too, but that's not where the windmills are. We put the windmills out in West Texas where there's nothing but jackrabbits and cactus, and there's very little obstruction. So we have and there's lots of heat, so we generate a lot of wind out there, and we're already using a good bit of it. I think almost all the utility companies are using 10% or more green. Yes? When we first start talking to car companies, here's what they tell us. We really are interested in green, but we don't want to pay any more for it. Okay? So I said, okay, thank you for being upfront, and we think that's okay. We think we can work with that. But I think the real driver is, in fact, they're very interested in more green products, and at least some of the people we're working with are very excited about the possibility of also doing something that would also help coconut farmers in developing countries. So in a way, it's a nice story because it's a win-win-win. There's no like you win and you lose, or you get a bigger piece because you get a smaller piece. No, I think everybody gets a bigger piece of the pie in this deal. If what? Would they pay a little more for this? The answer is I don't know. Would they want to pay a little bit more? The answer is no. They've already said that. But there is some PR value, and maybe we can also show in our case, if we have much better flexural modulus or flexural rigidity, then we could actually say, look, you don't need to use 1,000 grams per square meter. You can use 800. Now we can really be a lot cheaper in cost, even if our fiber is a little more, and we can lower the weight on your car. And that really sells, okay? So that's why I'm saying we're working hard at really pushing those properties up, and we're doing a lot of R&D to make that happen. There's a lot of interesting things you can do to keep pushing that up. But the higher that gets, the more the cost savings options are more than just doing a straight 1,000 gram per square meter felt for another 1,000 gram per square meter felt. If I can get the same behavior with 800, they're getting with 1,000, then there's some built-in opportunities there. And they love saving weight, too. I mean, they're worried about weight. They don't want anything heavier. They don't want anything more expensive. They told us that up front.
We'll have one last question here, and then we'll thank our speaker.
Okay.
So what's your funding? You said you had some funding.
Oh, did we get some funding? Yes, we finally have got some funding. And I'm supposed to always mention this. Okay. We had a SBIR Phase 1 grant for $100,000, and then we got a Phase 1 extension for another $50,000, both from the National Science Foundation and very competitive competitions where they fund maybe 15% of the proposals. Now that what we did in Phase 1 they were sufficiently happy with, we got Phase 2 funding to develop a supply chain for $500,000, again from the National Science Foundation. So if you have something that really looks like it could work and be beneficial to Americans as well as maybe to people overseas, then I think they're interested in trying to find things that work. We're also creating jobs. This year we will create 5 jobs at a lot less price than some of the prices I've seen in the newspaper. $3 billion or $3 million per job or something, We're creating jobs fairly efficiently, cost effectively. Before we finish, let me mention I'm going to be here until Tuesday, and I'm giving a talk Tuesday evening on a completely different topic. is there scientific evidence for the existence of God? And it will have nothing about coconuts, but it's another interesting topic. And so if you're interested in that, then I would be delighted to see you once again. Okay? Thank you so much for staying around on a Friday afternoon.
Dinner arrangements all set up?
I think so.
Okay, well, I wanted to thank you for coming. It
Well,
was
thanks.
a pleasure to make your acquaintance.
Well, likewise. I
And
enjoyed
maybe
visiting.
we'll be in touch in the future.
Okay, sounds
Take
good.
care.
Thank you. Oh, okay. I'm told these posters are already all over campus, so I should have said something. Well, maybe they just got put up today, but it's 105 Dartmouth Hall. I don't know where that is. Okay. Yeah, if you're not on campus, I should have. No, I was going to keep it. I liked it a lot.